Here at Crab Orchard Spillway with John Schoonover. I'm Carl Williard. We got Parker Schoonover on the video camera. But we're here today. We're going to shoot a video on stream gauging and actually show you the equipment we use to measure stream discharge in the field. We'll do it in two different ways. A real basic way you can do it is just with some type of floating object. And then we'll also show you how to use our velocity meter. You can see our Marsh McBurney. And then we also have a weighting rod that velocity meter will attach to right here. So we'll show you, demonstrate both of those. So let's first talk about why do you want to go out and get discharge of a stream? Obviously there's a lot of different uses of discharge data, looking at flood responses, also impacts of drought on water levels. So the main federal agency that's responsible for stream discharge measurement is the U.S. Geological Survey. So they have a series of gauges throughout the country on streams and rivers where they're monitoring stream discharge, and they'll go to a set cross section. It's usually some part of or a stable part of the stream or river channel, usually a relatively straight section, commonly like here, maybe near a bridge or a stream crossing, and that's where they'll come to measure stream discharge. And if you've ever gone on to the usgswater.gov, I'd encourage you to just check out that homepage. You can see all the different discharge measurements that the USGS does throughout the country. So if you're, for instance, going out canoeing or kayaking, you can check out, and some of these are in real time. So you can check out the discharge data on your favorite river, like over at the Current River or something like that, to see how high the water level is. And you may ask, well, how do we get this data in real time? They certainly don't have somebody out there with a weighting rod all the time and measuring discharge. But what they do, and the USGS, and we've actually had some students, a student of mine who did his master's thesis, Roger Hashmeyer, actually works for the USGS as he maintains their river gauge network in eastern Nebraska. But what he does, he'll go out and he'll actually physically measure discharge like we're going to show you today. But he also, every time he goes out to do that, he'll get an estimate of what the stage or water level is of that stream or river. And then he'll do that over a variety of different discharges and basically make a regression equation of those, of stage versus discharge, and that's called a rating curve. So then after that, you'll have a stilling well, which is basically just a corrugated steel pipe with a water level recorder in it. That could be a pressure transducer, it can be a floating pulley in there that monitors the depth of the river as that water level goes up and down. And once you have your rating curve developed, again, that's your stage versus discharge, you can take your water level data and plug it into that regression equation, and then that's how they get a continuous estimate of discharge without actually being there to measure it. So when you check out that usgswater.gov, go on there and look at that real-time data. That's estimated data coming out of those rating curves. All right, so Griffin is stretching a tape out, and this is for what we do if we had you out in the stream for the floating object method. And basically, we're just measuring the amount of time it takes for a floating object. You can use a water bottle or an orange or a stick, something that's going to float down the stream. And basically you're just measuring the amount of time it takes for that object to float a known distance. So Griffin has stretched out the tape, let's say 100 feet, and then John's going to be dropping a floating object, and we're going to time the amount of time it takes for that floating object to make it down the river that 100 feet. So how do you think we're going to get velocity from that? Like if you think, what would be a unit of velocity? Well, that could be, right, in feet per second in this case. So Griffin has 100 feet, for instance, and then we're going to time this floating object, and that'll be our second. So we take the 100 feet divided by the amount of time it took for that object to float, and there we got our first measurement of actually stream velocity. Now we're going to do that, if we'd be out in the field, we're going to do that in a couple different locations across the stream, because obviously velocity, as you see here below the spillway, is different in different sections of that stream, as Parker's showing you. So we're going to show, John's going to be dropping that object, and then when it gets to time 0, we'll start our clock. So we started, you can see that float, so we're monitoring time. And for instance, we generally do 100, maybe 200 feet. The longer, probably the better. So now we're at the end. So this is a short run just for demonstration purposes. So we take that 10 seconds in this case. So you'd have your 100 feet divided by your 10 seconds, so we get 10 feet per second, which is moving pretty fast, which it would be in this part of the channel. Now again, you'd have to do that at multiple locations across that stream channel, and then you'd average those together to get an average velocity. Now, we didn't talk about discharge. What are the units of discharge? Well, that's a volume of water per unit time. So in English units, that would be cubic feet per second. So we just got velocity from our floating object in feet per second. So how do we get our area? Well, we'd stretch our tape. We got to measure two things. You can guess what they are. It's going to be the width and depth of the stream. So we stretch our tape across, get a width in this section, and you may want to do in that 200-foot reach or 300-foot reach, you may want to do that 5 times and get an average width. And then we take our wading rod and we measure a depth, and we go across a cross section. We may do this 10, 20 times to get an average those together to get the average depth. You can see here as Parker zooming in, you can see how this wading rod works. This is an English wading rod, so it's in English units. You can see these lines, these demarcations. So every line is 1/10 of a foot. So there's 1/10, 2/10, 3/10, 4/10. So every half a foot is 2 lines. Then we go up again. Every triple line would be a whole foot in this case. So it's not in inches. Some people get confused because there's only 10 demarcations there. So it's in tenths of a foot. So we'd measure that, for instance, right here, we get a depth of 1/10 of a foot. And then we'd average that. And remember, what is a cross section? Well, that's straight across. So we're getting a cross-sectional area. Once we get that average width times our average depth, we're going to get our cross-sectional area. What do we do with that to get discharge? Well, we just simply multiply your cross-sectional area times your velocity we got with the floating object, and there you got discharge. So that's a real crude way to get discharge, but we've had students in the past that have served overseas. For instance, in Afghanistan, that he told me he used the floating object method to get a quick estimate of discharge before they drove across some of the streams that they were trying to traverse to make sure there wasn't too much discharge and they could safely cross. So it is a nice, simple way. You don't need equipment. All you need is a floating object and a tape measure, and you can get an idea what the velocity is.
Talk a second about the correction factor.
Okay. Yeah, thanks, John. The correction factor, so we had that floating object moving down there. And of course, you notice, of course, it's going to float up on the surface, right? And if you think about the velocity profile within the depth of the stream from top to bottom, it's going to be, where's it going to be highest? It's going to be up top, right? That's where the water's moving the fastest because you have least impact of friction. on the floating object. Where is it going to be the lowest? Down at the bottom, right? Because it has the most interaction with those frictional surfaces, the rocks you see here and the weeds and so on. So it's approximately, your average depth is going to be, and you'll see that come into play with this, is 4/10 from the bottom. But what we do in the floating object to get an average approximation of the velocities, we take the floating object velocity and multiply it by 0.7 to get an approximation of the average velocity, because that surface velocity is going to be much higher than your average velocity.
All right, so I'm going to go over the same thing with the floating object, just on paper, if you will, but this is going to be sand. So I'm going to draw this. If this was our creek channel right here, we're going to measure velocity. So if this is a 100-foot reach, we're going to measure velocity at 3 points. Like Dr. Williard said, we're going to do left bank, right bank, and in the center. So we're going to get those 3 velocities and take an average. The 3 widths he was talking about was, we'll take a width here, and a width at the downslope area. So what we're trying to do is calculate the cross-sectional area. So again, like he said, we need width times depth. So along this width line, we'll take 10 depth measurements. We'll also take 10 depth measurements along the middle one, and then 10 depth measurements across the top. So we're going to take the average depth times the average width to get the average cross-sectional area. And then we have the average velocities that we corrected by the 0.7 factor. So multiply that velocity average by 0.7. Then you multiply all 3 things together, the velocity, the cross-sectional area with the width and the depth, to get total Q, or total discharge. So that's our discharge estimate in cubic feet per second or cubic meters per second, whatever units you used. So now we're going to talk about the midpoint method, and this is where we're using the Marsh-McBurney or Price Pygmy meter to measure velocity. So again, I'm going to draw a stream channel. This time it's a cross-sectional area of a stream channel. So water's flowing this way. First thing we're going to do is stretch a tape across the stream. And then we're going to try to divide this channel up into 20 equal increments or subsections. So since this isn't very fine resolution, I'm going to draw fewer than 20, but you'll get the point. So what we're going to do here, kind of like we did with the floating object method, we need to determine what the cross-sectional area is. And to be more accurate, we take more subsections. So this cross-sectional area is obviously different than the next. So at each one of these, the reason we call it the midpoint, we go to the midpoint right there, and we'll measure depth and velocity. And then we know our 20 increments are a certain width. So if they're 1 meter increments, if this was a 20 meter wide stream, our width would be 1, then we'd have a depth, and then 6/10 up off the bottom we would have a velocity. And Dr. Williard will show you how that works with the wading rod. So we'll get a cross-sectional area here, a cross-sectional area here, and a velocity, width, depth, velocity. All those are going to equal discharge. So at the end of the equation, we're going to have to sum all these total discharges, or all these discharges for these subsections, to get total discharge of the entire stream channel.
Here we are, we're out closer to some of the main velocity in the channel. And you can see, again, we'll repeat what we did back there. First thing we do, we go to our, in this case, 0.03 meters, and that'll be the middle of this subsection. And first thing we do is what? Well, we look down, we see what the depth is. What's our depth there? Here we got to pay attention to the double lines, right? Because we're in a deeper area. So you got a double there. That's 0.5, 0.6, and then we're right around 0.7 of a foot. So how do we do that on our top setter again? Well, we take the 0 line, press this in, and we're going to move it up where? To the 0.7. And then again, we put the ball directly into the flow. So now we're measuring that flow in the middle, and you can see in that, I don't know if you can see in that water column, but you can see the bulb in the middle of the water column pointed directly up. And then we're reading velocity. So on here you can see Parker, on this case it changes every 5 seconds, but until you get a number that's pretty stable. So we're sitting around 0.57, 0.58, 0.62. There's a 0.64. So probably about 0.5. There's a little bit lower. So it does take time to stabilize. So I'd say around 0.55, 0.58 would be our velocity. Again, we got a meter, so convert that to feet. And then our last number is our depth. In this case was 0.7 feet. So multiply those two or three together, and we're gonna get discharge in cubic feet per second. And then what do we do to get the total discharge of the stream? Well, we're just gonna add up or sum the subsection discharges, like we showed 2 examples here. We sum those together to get the total discharge. Don't make the one big mistake students make when they do this exercise is you average the subsection Q's instead of sum them. And that's not what we want. That would just be the average subsection discharge. We want the total discharge of the stream, so you just add up all those together and we're gonna get our total stream discharge using the Marsh-McBurney meter and our top setting weighting rod. All right, so you can see here we have a tape stretch to the water's edge, and we'll be doing this to get our midpoint method of the stream gauging with our weighting rod and Marsh-McBurney velocity meter. I wanted to show you first the velocity meter. You can see, you want to point that, you see the flow direction. So you want to point that bulb directly. Here we're in a slack water part, but you want to point that directly upstream where the majority of your flow would be hitting that bulb. And you see on the video here, can you see the 3 circles? There's 3 black circles there on the front face of that bulb. And what that puts out is an electromagnetic current into the water. And using Faraday's law, as the velocity or the water travels across that electromagnetic current, that's converted to a velocity. So this is a very rugged piece of field equipment. The other one John mentioned is the Price Pygmy meter. That's actually cups, rotating cups that spin around, and you have a counter on there, so you basically count every revolution, and that's converted to a velocity. But this is nice when you're in the field because it's very rugged. You're not gonna have problems in terms of this messing up and if you're knocking around on something. So John introduced the midpoint method. So if you see the tape here, water's edge is right at 5.8 meters, for instance, in this example. So let's say we did 20 cross sections, and let's say it was 20 meters wide, the whole stream. So we'd break each subsection then into 1 meter, because we're gonna have equal width increments across the stream channel. So if we'd start here at this bank, and we got 5.8, and we're going to the middle of the first section, and that first section is 1 meter, where should we go to make our first measurement? You can think about that. Well, we should go a ½ meter in, right, from the bank. So we'd go to the 5.3, so right here, and that's where we'd make our first measurement of water velocity. Again, in the middle of that first meter width increment. So the first thing we do when we measure velocity, before we measure velocity, we're going to measure the depth at that location at 5.3. So we're going to raise this up so we can see the depth, and I don't know if Parker can bring the video in there. You can see, and we'll lift this up a little bit. That's basically at a little bit above 0.2. So that would be 0.2 feet would be our depth. Now, as we come in here, you see these zeros and 1. Here, I'll put it down. See the 0 there by my thumb? And then the 1. So what you do, if you are in depth less than a meter, or a foot in this case, because we have the English rod, we're going to use the 0 line. And we're going to set it, so you can see I can move that, I push that in, and I can set that wading rod, right? I can move it up and down. So we were at, what were we at, Parker? 0.2 of a foot, right? So I'm going to put the 0 at the 2. And basically that does my math for me, because remember back to the earlier discussion, we want to get an approximation of the average velocity, and that's approximately 4/10 from the bottom. So if we get 4/10, so we'll do the math together. We take 4/10 times 2/10, the overall depth, right? We should be at 0.08, approximately 0.1. And we'll check, basically the top setter does that math for you. So if you put the 0 at the 2/10 depth, we should be at 0.08 or around the first demarcation, and lo and behold we are. Because you can see, if I move this up, there's that first demarcation. So we're down, we're basically at the bottom. That's about as low a depth as we'll measure. You put that, when you measure, you got to make sure the bulb is submerged, right? And you're going to turn on your velocity meter. So you can see in here on the display, we're not getting any flow. Well, we got 0.05 there, 0.07. It's a very little flow near, we're in a pretty slack water situation. But we'll show you another one. So once you get that, so we had 0.05 feet per second. We got the width, right, which was 1 meter for our subsection. We can convert that to feet. And then what was our depth? 0.2, right? So as John said earlier, if we take all 3 of those measurements, width of 1 meter, depth of 0.2 feet, and velocity of 0.05 feet per second, we first convert the meter to feet, then we multiply those 3 together. What are we going to get? Well, we should get cubic feet per second. And that's the actual discharge in this meter subsection. And then we're going to do it 20 times all the way across.